Assalamualaikum warahmatullahi wabarakatuh and good morning. So today we are going to continue our discussion about compensator that we design using word plot. So in the previous lecture, you are already learned about how to design lag compensator based on this word plot. So now today, we are going to discuss about the other method, which is lead compensator that we use to improve the transient performance of the system. Okay, why we design this lead compensator? So in designing lead compensator via word plot, so we want to change the phase diagram, increasing the phase margin to reduce the percentage of overshoot, and increasing the gain crossover to realize a faster transient response. So in this design, we only focus on this transient part. So this is the procedure how we can design this lead compensator. So first we have to find the closed loop bandwidth required to meet the settling time, peak time, or rise time requirement, or all these parameter. So as you can see, the parameter that we are going to improve to make sure the performance will meet is the parameter that refer to the transient part. Okay, second, set the gain K of the uncompensated system to the value that satisfy the steady state error requirement. Okay, before we design to improve this transient part, so we have to make sure the uncompensated system value for the steady state error should be satisfied. Okay, next, procedure number 3, plot the both magnitude and phase diagram for this value of gain and determine the uncompensated system phase margin. And this is the same procedure as previous lecture. So you just plot this both magnitude and both phase magnitude, and from there we can determine the value of gain margin and phase margin. That is we call uncompensated system performance. So from there we improve the system based on the requirement. Okay, next, find the phase to meet the damping ratio or percentage of overshoot. These two parameter is depend to each other because based on this damping ratio we can find this overshoot and vice versa. Okay, then evaluate after we get this damping ratio and percentage of overshoot that we required. Then evaluate the additional phase contribution required from the compensator. Okay, step number 5, determine the value of beta for the lead compensator required phase contribution using this formula. This V maximum equal to inverse tangent 1 minus beta divided by 2 third beta. Or this equation also same with if we use sine function like this. Inverse sine 1 over beta divided by 1 plus beta formula. This is the modulus for GC J omega max equal to 1 over beta. Okay, step number 7. After we get all these parameters, so we have to determine the new phase margin frequency by finding where the uncompensated system's magnitude curve is the negative of lead compensator magnitude at the peak of compensator phase curve. Next, after that, we have to design the lead compensator's break frequency where we use this formula omega max equal to 1 over T times Z beta. Okay, to find this T and also breakaway frequency. Next, we have to reset the system gain to compensate the lead compensator gain. So we will get the new value of gain here. And next procedure, so we have to check the bandwidth to be sure that the speed requirement in step 1 has been met. Okay, and then after that we can simulate to ensure that the result that we get after we design is follow the requirement. If not meet the requirement, so we have to redesign again. That is the 12th step that how we can design this lead compensator using this board plot. Okay, this is the transformation for the lead compensator where as you can see here, the formula for lead compensator is same if we compare with the time domain analysis using that what you have learned before root occurs technique. So which is the transformation for this lead composition is one over beta, which is this one is equal to k gain s plus 1 over t, and this one is equal to 0, and s plus 1 over beta t, this one is equal to all that we add to the system when we design this kind of controller, where beta should be less than 1. This is what we were going to do when we design the lead compensator. So in which we have to reshape this uncompensated system and become like this because we want to improve the transient. And also for this phase, when we design this the lead compensator, so based on this value of 1 over t and also 1 over beta t, so we can draw this phase plot like this, and then this plot will combine with the uncompensated system, and after we combine, so we get the result become like this. And this is what we will do when we design this lead compensator. So after this curve change to the other curve, after this one change from here to here and also from here to here, so automatically the phase margin and gain margin will change, and also the performance of transition part will also change. Now let us look at this example. Given the system as shown in figure question 1.4, which is referred to this system, for the unity feedback GS equal to 100k divided by this denominator. Find the value of k if velocity constant kv is equal to 40. Then design a lead compensator using frequency response technique to improve the transient response to be 20% overshoot and peak time of 0.1 with peak time of 0.1 second. Next, find the compensated open loop transfer function. After we design this lead compensator, we can obtain this compensated open loop transfer function. And after you get this open loop transfer function, we can draw the bot plot with this compensated open loop transfer function become compensated bot diagram. Okay, to solve the first problem, which is find the value of k if velocity constant kv equal to 40, we just use the formula for static error constant. In this case, kv, so that means we refer to velocity constants. So for velocity constant, the formula same like what you have learned in control system fundamental, which is kv equal to limit s to 0 s ts. So that means we have to settle this equation first. This s and this s we have to cancel each other. After we cancel this one, so the equation become only limit s to 0, 100 kV divided by s plus 36 times s plus 100. So when we put this s equal to 0 into this equation, so the result become like this. So from here, we can find the value of this a, which is equal to 40 times 36 times 100 divided by 100. Simply we just uh, move this part and this denominator to here and become like this, and then this one move to here become like this, and that's mean divide by 100. So the result become k equal to 1440. Okay, so that the uncomposite system with this kv equal to 40 is become gs equal to 144,000 divided by this denominator. And next, based on requirement, so we have to make sure the percentage of overshoot for this after we design this lead compensator should be not more than 20%. So based on that, we can calculate the value for damping ratio, which is equal to this formula. So this is the same formula that what you have learned in the previous control system fundamental. So you just use this formula and then put this 20% inside this formula. So this one 0.2 because of 20 divided by 100. So just put here, and then the result for this zeta equal to 0.456. Okay, before we can design the lead compensator, so we have to plot the board plot for the uncompensated system. So after we plot the both plot for magnitude and phase, so we get the gain margin and phase margin is equal to 9.5 dB and 22.5 degree respectively. So this gain margin occurs at 64 radian per second, and this phase margin occurs at 37 radian per second. Next, the compensated phase margin can be calculated by using this formula. Just use the zeta that we have calculated before at this one, 0.456. So we just put this value into this equation, and then we get the compensated phase margin equal to 48.1 degree. Okay, so but this is not exactly the composite phase margin, so we have to do correction. So we have to use this formula where the final result for this phase margin of the composite system become this value 48.1 minus the uncomposite value plus 10 degree. So after we calculate, so we get this new phase margin for the composite system is equal to 35.6 degree. Based on this value, and then we have to find the value for beta using this formula, where in this case Vm that we calculate from this value of beta is equal to this phase margin for the lead compensator. So from there we just put this value 35.6 here, and then from there we can find the value for this beta. So after we get the value for this beta, so we can use to find the value of k, so which is equal to 1 over beta. We just put these results, this beta equal to 0.264 after we calculate using this formula. So we just put here, and then k is equal to 3.8. So where k equal to 3.8 is the gain required to keep the DC gain for compensator at unity, where in dB this value become 20 log 3.8, which is equal to 11.6 dB. Okay, using equation GC J omega max equal to 1 over Z beta. So we just put this beta inside this equation. So we get GJ omega max equal to 1.946. Therefore, the lead magnitude is 20 log 1.946, which is equal to 5.8 dB at omega maximum. From this lead magnitude value, so if we look at back at uncomposite work plot, so the value for 5.8 is around here, which is about 52 radian per second, and that's why we get this value 52 radian per second. So this 52 radian per second is considered as a omega maximum. Okay, now we can find the lead compensator transfer function using formula GC lead of S equal to 1 over beta times with these zeros and S plus 1 over T. Okay, this one is a component for zeros for this lead compensator divided by this denominator, which is S plus 1 over beta T. So this is referred to the poles for the composite system, where 1 over beta, because we already calculate the value for beta, so we just use this formula to get this 1 over beta. This is considered as a gain, and as I mentioned before. So 1 over t is referred to this equation omega max times with this set beta. So omega max we already obtained from here, from this 5.8 dB, so which is equal to 52 at time with this search beta. We just put this value for beta here, and then we get the result become 26.7. And also based on this 1 over beta and 1 over t, so we can obtain this 1 over beta t, just multiply this value and this value, and then we get 101.46. So therefore G of S for lead compensator is equal to 3.8 times with S plus 26.7 divided by S plus 101.46. So this is the transfer function for the lead compensator that obtained from this design. Next, we combine this GC of S lead compensator with the system. So the overall GS GC become like this. Okay, that means we have to combine this transfer function with this compensator transfer function. So this is the magnitude plot for this compensator function. So based on our calculation, so 1 over beta t is 101.46. The magnitude start from 0 here till 1 over t, and from calculation we got this 1 over t is equal to 26.7 radian per second. So we start from this 26.7 radian per second. This magnitude compensator will increase 20 dB per decade till we get this 1 over beta t, which is at 101.46 radian per second. And after that, this magnitude remain at 0 dB per decade. So after we put this compensator component, we combine this component and this uncompensated system, and the result become like this. That means we start from here, we have to add this component with this component. So this one become cancel. So this result become like this. I just remain at 0 dB per decade. Okay, at this point, and because this one is 40 dB per decade and this one is 20 dB per decade, the slope become 20 minus a negative 40 become negative 20 dB per decade, and that's why we get like this. And this one is horizontal line, and start from here, this one is 20 dB per decade. Okay, until here, and at this point, so this one is equal to 60 degree per decade, and this one is 0 dB per decade. So starting from here, the slope become 60 dB per decade, and that's why we get the result for the system with composite system with lead compensator like this. Also same for this phase plot. Based on this equation, so we have to draw the phase plot for this compensator component, and then we combine the compensated component with this uncompensated phase plot, and then the result become like this with some different with at this area after we combine the uncompensated system with the phase lead compensator. This is how we can design the lead compensator by using word plot. Okay, thank you. That's all for today. So hope you can understand, and if still have a problem, you can discuss with your friend. And if still have a problem, so then don't hesitate to WhatsApp me to ask the question. Thank you.